All right, let's jump right into it. Welcome to The Explainer. Today, we're unpacking one of the most vital and, honestly, fascinating topics in modern software design: zero trust security in microservices architecture. If you've ever wondered how these massively complex cloud systems actually keep our data safe when the old-school network walls have basically vanished, well, you're in exactly the right place. We're going to decode this whole thing step by step, breaking down what can feel like a totally overwhelming topic into a clear, structured system.
Never trust, always verify. Yeah, I know, it sounds a little intense, doesn't it? But this is the stark, unyielding reality of the zero trust mindset. Back in the day, if you were inside the corporate network, you were considered a friend. You were just trusted by default. Today, well, that assumption is a massive vulnerability. In a modern microservices architecture, every single request, every service, and every user has to continuously prove exactly who they are and what they're allowed to do. Literally nothing gets a free pass.
To achieve this level of paranoia, and I absolutely mean that in the best way possible, architects have built a truly robust defense system. We're talking about an intricate 10-layer security model. 10. What's really striking here is just the sheer scale of it. 10 distinct layers of defense all working in perfect harmony. It might sound like a lot to take in, but don't sweat it. We're going to build this layered fortress together, piece by piece, so you can see exactly how it all interlocks.
So here's our roadmap for today. We'll start with the zero trust philosophy, then securing the outer edge, followed by trust no internal service. After that, we'll hit rules, secrets, and zones, and we'll wrap it all up by tracing a complete request journey.
Okay, let's dive into part one, the zero trust philosophy.
So in a traditional network, what we usually call the castle and moat model, you build a huge firewall and just assume everyone inside the castle is perfectly safe. The problem? If an attacker breaches that wall, they've got the run of the place. Zero Trust flips this and treats the internal network as potentially hostile. It's kind of like a VIP hotel. Just because you made it through the front lobby doors does not mean you can waltz right into the penthouse or the kitchens. Getting inside is literally just step one. You are still completely untrusted.
Moving right along to part two, securing the outer edge. Which brings us to our first structural zone, layer 1, user identity. If our system is that VIP hotel, the JWT, or JSON Web Token, is your digital hotel keycard. When you log in, usually doing your multi-factor authentication, a corporate identity provider issues this JWT. It's a brilliant example of packaged trust. The token carries these verifiable claims: your user ID, your roles, and an expiration time. You aren't just pinky swearing, "Hey, I'm John." You're presenting a cryptographically signed card that proves it.
And here is the absolutely crucial takeaway. Trust lives in the token, not the client. This is a huge shift in thinking. The back-end services do not care if you're logging in from a shiny new corporate laptop or some random computer at the public library. The device itself holds zero inherent trust. The whole system relies entirely on verifying the cryptographic claims embedded right there in that token.
This flows perfectly into layer 2, the API gateway. Think of this as the heavy security door at the front of our hotel. It receives all the incoming traffic, and its absolute first job is to validate that JWT before routing anything to the backend. It also handles rate limiting to prevent spam and acts as a web application firewall, a WAF, to block attacks. It logs every single request. Only if everything looks completely flawless does it forward that token downstream.
All right, into the internal network we go with part 3, trust no internal service.
Once we're inside the walls, we hit layer 4, mutual TLS, or MTLS. Now, you use standard TLS every day on secure websites, right? The server proves its identity to your browser, but MTLS is a two-way street. It's the cryptographic backbone of how these services talk. When microservice A talks to microservice B, both sides have to present certificates to validate each other before a single byte of data is exchanged. By demanding this two-way verification, MTLS completely stops impersonation dead in its tracks. But wait, how does a random piece of code even get an identity to put on a certificate in the first place? Enter Layer 6, Service Identity, powered by frameworks like Spiffy. That stands for Secure Production Identity Framework for Everyone. It assigns a highly specific, cryptographically verifiable identity to every single microservice. So instead of just an IP address, the payment service gets an identity format like payment.default.svc.cluster.local. Communication is then explicitly allowed or denied based on those exact identities.
All of this cements the golden rule of Layer 3. Authenticate every hop, not just the edge. Back to our hotel. You don't just check IDs at the front desk. You check them at the elevator, in the hallway, at the room door. The customer service, the payment service, the inventory service, they never, ever blindly trust each other. They verify identities at every single hop.
Let's pivot now to Part 4, Rules, Secrets, and Zones.
So let's look at Layer 8, Policy Enforcement. Meet OPA, the Open Policy Agent. This is a centralized policy engine using a language called REGO to make those hard, allow or deny decisions. Think back to that JWT keycard. A service might verify the signature on your card, but then it asks OPA, hey, does this specific cardholder actually have the right to look at this specific file right now? OPA is basically the brain evaluating rules at every level, enforcing policies without developers needing to rewrite the actual application code.
And how exactly does OPA make those decisions? Through Layer 5, Authorization. Role-based access control, or RBAC, is pretty basic. You're an admin, therefore you get access. Simple. But Zero Trust thrives on ABAC, attribute-based access control. It's incredibly granular. An ABAC rule might say, if the user is in finance, and they are on a managed device, and it's during business hours, then allow access to payroll. Actually, if even one of those attributes fails, boom, request denied.
Then we've got Layer 7, Secrets Management. Things like database passwords and API keys must never be hard-coded. No way. Instead, a microservice authenticates with a secure vault, like HashiCorp Vault. It receives a short-lived, temporary secret just to do its job. Because these secrets are dynamically generated and automatically rotated, even if a hacker somehow steals one, it becomes utterly useless in a matter of hours, if not minutes.
But let's say the absolute worst-case scenario happens and an attacker compromises a service. That is why we have Layer 9, Network Segmentation. The network is chopped up into fiercely restricted zones: public, gateway, business, payment, data, and management. Traffic between these is locked down by firewalls and Kubernetes policies. By eliminating the flat network, we isolate the attacker. They might breach a public service, but they can't move laterally into the payment or data layers. We lock down the blast radius. Finally, Layer 10, Continuous Monitoring. Zero Trust basically operates under the core assumption that you've already been breached. The system is always watching. It relies on stacks like Prometheus and CMs to ingest telemetry in real time. It's constantly hunting for anomalies, like sudden spikes in auth failures, weird token errors, or privilege escalations. The moment something looks sketchy, alerts are fired off.
All right, bringing it all home with Part 5, the complete request journey. Now that we've got all the puzzle pieces, let's look at a day in the life of a secure request. Step 1, you log in with MFA. Step 2, the identity provider issues your JWT keycard. Step 3, your request hits the API gateway. Step 4, the gateway aggressively validates that JWT. Step 5, the internal microservice gets the request and validates the JWT again. Step 6, it asks OPA for ABAC authorization. Step 7, if it needs to talk to another service, it uses an encrypted MTLS tunnel. And Step 8, it pulls a temporary password from the vault. And Step 9, the whole thing is logged and monitored. It's a flawless, seamless chain of verified, encrypted steps with zero implicit trust. Which leaves us with this one massive question to think about. In this architecture, literally every single step is verified, encrypted, and logged. We don't rely on walls anymore. We rely on constant cryptographic proof. So look at your own systems and ask yourself, if your perimeter fails today, what happens tomorrow? Does the attacker get the keys to the kingdom, or do they hit a brick wall at the very next microservice? Thank you so much for joining me on this explainer. Keep asking those tough questions, and I'll catch you next time.